Bum, 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 bum. Guess who's back, boys and girls? That's right, Mr. Howdy. What's up? Hope everybody's been having a good no school, not break. We're still doing stuff, right? Over the past couple of days. But we're getting back into it. Hopefully you've been doing your Khan Academy and reviewing some division, but we're going to continue to move forward. Last we talked about, before the outbreak in the end of the world, we talked about solving using polynomial identities, and we were looking at how we could factor those. So now we're going to prove these polynomial identities. So we're not only going to show how we can factor them, but why they make sense. So that's why we're going to prove them. So I have a little clip for you today to be prepared to do your little exit ticket at the end. So here we go. Bet you thought you'd seen the last of me. Wrong. I'm here. I'm back. What's up? So first, if you remember this beautiful thing, we have all of our different identities, different factoring techniques. Difference of two squares, sum of two squares, difference of two cubes. There's a bunch of different ones, right? Right. Okay, so there's our list. If you needed to take a screenshot of that, take a picture of it, there it is. I'll give you 1 second. All right, 1 second's up. So if you need to do that, come back to this slide. The identity, since we're talking about proving identities, we should probably know what an identity is. An identity in an equation that it is an equation that is satisfied by any number that replaces the variable. So no matter what number you put in, it'll be true, basically, is what it means. So like, here's a very basic identity maybe. X equals X. No matter what you put in for X, it's going to be true. If I put 0 in for X, 0 equals 0. If I put 4K in for X, it's going to be 4K. No matter what I put in for X, it is still going to be equal to X, okay? So an equation that is satisfied by any number that replaces the variable, no matter what you stick in there, it's still going to be this. It's going to be equal. They're going to be the same, okay? So let's do a couple examples. I got 2 for you today and 1 for you to work on. So here we go. Example numero uno. So if you remember, this is the difference of 2 cubes. I'm not making this up. It is right here. Difference of 2 cubes. Oh yeah. So we want to prove that this is true. We see right here that it says that they're equal, but why are they equal? We want to figure that out. So let's see why they're true. You could technically break these apart and work from either way, but I think it's easier if we work from this side and multiply some things out so that we can make it look like this. So essentially when we're proving these, we want this side over here, or one of the sides, to look equal to the other side. Okay, so if we start with the right side, then basically all we have to do, this isn't that difficult of stuff, it's not rocket science, we just have to multiply them out. So let me get a little highlighter. Here, this one's for Brooklyn, because she likes to use those horrible pencils that you can't actually read, or those pens. So we're going to take X times the first term, X times the second term, and X times the third term. Okay, let's do another one. Y times the first term, Y times the second term, and Y times the third term. Okay, so we're going to multiply all those in. We're going to FOIL, essentially, we're going to FOIL all of those. We're going to distribute all of those in. It's not really foiling if there's more than four terms in there, but still, we're going to do that. So let's do X times X. X times X squared is going to give me X to the third. Let's get a smaller marker. That's a little too big. X to the third. Okay, that's these first two right here. This one times that one. Okay. Then the x times xy would give me what? Riley? Nobody? Okay, cool. X squared y, right? Okay, and then x times y squared is the last one. So it's going to be plus xy squared. Okay, so now we're done with our x's for right now. So essentially, if I wanted to, I could just kind of mark those off and be like, okay, they're done for now, bye. Now let's do our negative y. Make sure you keep that negative in there because this is not just y, this is negative y. Okay? Minus y, negative y, same thing. This is negative y. So negative y times x squared is going to be negative x squared y. Negative x plus negative y times xy is our next one. Let me highlight that so you see where I'm looking. Here, right, is going to be negative xy squared, and then negative y times y squared is going to give me negative y cubed. Okay, so we have this big old mess right here, but we're still saying that it's equal to this left side. Okay, so let's prove that it is equal to that side by simplifying this. Okay, so can I combine x cubed with anything here? Can I combine it with that? Nope, 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 nope. Can't combine it with any of those things. Any of those terms. Whoops, go back there, little 3. Redo. Okay, so I'm just going to bring it down. Bring it down. All right, and then x squared y, can I combine this with anything? It's got to look exactly like this. We have to have an x squared and then a y. It can have a coefficient in front of it here. It can be negative or whatever, but it has to be x squared and times y. Is there anything similar? Well, I see one right here that's an x squared y. So that means that I'm going to combine x squared y minus x squared y, because that's a negative, right? So x squared y minus x squared y is going to give me 0 x squared y. We really don't even have to write that. And then next term, so we've kind of, let's highlight what we've dealt with. We've dealt with that. We've dealt with this. We've dealt with that. Next is this xy squared. Can that combine with anything? Of course it can. It can combine with negative xy squared. So xy squared minus xy squared is going to be 0 xy squared. And then left all by its lonesome, I won't say who this is, all by its lonesome is negative y cubed. So we're just going to bring it down. So you might notice that right now we have x cubed plus 0x squared y plus 0xy squared minus y cubed. Well, these are both being multiplied by 0, so we can cancel these out basically. 0 times all of this is going to be 0. So we're left with x cubed minus y cubed. And that had to be equal to what? We wanted it to be equal. We were showing that it was equal to x cubed minus y cubed. So at this point, we are finished. We've proven that these statements are equivalent to each other. Okay, so the left side over here is equal to the right side over here. That's what we were trying to show. Okay, so number 1 example complete. Number 2 example, here we go. We're going to do the difference of squares. We can do the exact same thing. We need to make sure that this side is equal to that side. You can work from left to right or right to left. You can simplify whichever one you want or expand whichever one you want. I would prefer work with the bigger side, the one that's got more terms on it, and multiply those out so that you can make it look like this. It doesn't take much thinking to multiply. It takes a lot of thinking to try and pull things out and divide. So if we did that, we would want to essentially just FOIL this. I mean, this is a legit FOIL. It's distributing, but it's also foiling. So a times a and a times negative b, and then b times a and b times negative b. Okay, so if we wanted to write these out, a times a is going to be a squared. A times negative b is going to be negative ab. B times a is, I'm just going to rewrite this in alphabetical order. B times a is ba, but it can also be flipped to be ab. And then b times negative b is negative b squared, okay? If we want to combine like terms, we can say, well, a squared is by itself, so I'm just going to drop it down. Negative ab and positive ab plus ab are put together, so I can combine these two. So I've dealt with those, and that is 0 plus 0 ab. And then lastly, I have negative b squared. So negative b squared comes down by itself. 0 ab is the same as 0, right? So we can just get rid of that. So we can bring down a squared minus b squared to be what this right side would be if we would multiply and simplify. Okay, so that's what we did. Is that proving our identity? Yeah, it is, because we have that this is equal to each other, equal to each other, equal to each other. So that means that a squared minus b squared needs to be equal to a squared minus b squared, which we've shown. We've proven this identity in example number 2. Okay, at long last, I told you that I would give you one example to work on. If I were you, I would write this on a piece of paper. It's going to be one of these. I would write it on a piece of paper and take a picture of it to upload it. That would be easier than trying to put in squareds and all of that stuff into the Google Classroom and all that. So here is your turn. Oh, yes. Yes, fabulous. Okay, your turn. So work on this one and turn this in for your exit ticket. So you want to show that a plus b squared, all of that squared, is equal to a squared plus 2ab plus b squared. Get to work. Let's go.